Hi, I am Seth Grover. I am the maintainer of Malcolm, the Network Traffic Analysis Tool Suite. Um, Network traffic analysis is all about getting to the important stuff as quickly as possible. There's a lot of open source and proprietary tools out there for analyzing raw packet capture or pcap files. Wireshark, Network Miner, Grassmarlin, um, but analyzing pcap sets that are large or from complex networks with many tools is difficult uh, because often tools that handle raw pcap data struggle to handle packet capture files that are larger than maybe a few hundred megabytes or gigabyte or two, depending on your system resources. Um, so today we're going to talk about Malcolm, a tool that was developed and is developed at the Idaho National Lab with the support of the United States Department of Homeland Security, CISA. You may be familiar with some or all of the tools that make up Malcolm because they're open source and they're all generally in use in the security and network traffic analysis community. But what Malcolm provides is a framework of interconnectivity for these tools, which streamlines network traffic analysis and helps you bring all that important stuff to the foreground as painlessly as possible. So that's what we're going to talk about today in this video is using Malcolm to gain insight into both link layer and application layer network traffic. Before we jump into our discussion about Malcolm and some of its primary components like Zeek and the Elastic Stack and Archime, let's take a minute and talk about intrusion detection systems so we can get an understanding of what these tools do and how they fit into the threat detection landscape. When talking about intrusion detection systems, usually you're going to be talking about tools in one of two categories. Host intrusion detection systems, or HIDs, utilize a native agent that runs locally on individual hosts and endpoints on the network. And these agents monitor, not only maybe network traffic and stuff at the device NIC level, but also track modifications to system files or monitor user authentication events, configuration changes, and report these events to a central manager for alerting and reporting. But host intrusion detection systems is not what we're going to be talking about today, as it's not really the main focus of Malcolm. There are plugins that you can use to get host data into Malcolm, and maybe at some future point we'll put together a video that'll instruct you how to do that. But for now, we're going to be talking about the other category of IDS, which is network intrusion detection systems, or NIDS. Network intrusion detection systems are generally passive and out-of-band programs or devices that capture and analyze network traffic at strategic points in your network in order to monitor traffic among devices in the network or between devices on the network and the outside world. So a couple of different ways that we can do this. The monitoring and analysis can be done concurrently. In other words, analyzing the traffic and forwarding it along capturing the traffic and then forwarding it along for analysis as it's captured. Or the other way is the network traffic can be analyzed after it's been captured in the past, right? We can capture it first with whatever set of tools we want. Matt, we're going to talk mostly about the latter today. Just for our examples, I'll be importing pcap data and then analyzing that pcap data rather than using a live network sensor to capture and forward that data. The Malcolm project does include a Linux distribution called Hedgehog Linux that's kind of a stripped down Debian based Linux that has these capture tools and easy configuration for those capture tools to set them up and capture and forward to Malcolm. There's another one of the videos on the Malcolm Network Traffic Analysis YouTube channel that talks about how to set up Hedgehog and Malcolm and set up that forwarding together. But today we're going to talk about more of the I've already captured, I've got some pcap, and I want to upload and analyze it with Malcolm. One other good important point about IDS is it's generally passive, meaning that it shouldn't alter the network traffic itself as a side effect of its analysis. There are systems out there that actively drop suspicious network traffic, and those are called intrusion prevention systems, or IPS, instead of intrusion detection systems, or IDS. And it's important particularly in networks with critical infrastructure. One of the focuses of Malcolm is industrial control systems or critical infrastructure networks with OT protocols. While it's perfectly suitable for using in a purely IT network, that's fine. But particularly on OT networks, it's important that we don't go knocking things over as far as network services go, because that may be critical infrastructure, right? And so it's important that IDS is done out of band and in a way that won't influence the network traffic itself. So let's talk about some of the different approaches to IDS. Each has its strengths and weaknesses, I guess you could say. First, there's signature-based detection, and this is what you're familiar to in the context of like a antivirus. An antivirus program, it has or a malware program that recognizes malware based on some pattern or signature in the malware itself, and then it has a list of predefined patterns that it's looking for. And when it finds a file or traffic or whatever that matches one of those patterns, it flags an alert as malicious behavior. While signature-based IDS is great for known attacks and it's usually efficient as far as resource utilization goes, it's not generally effective at detecting novel attacks because it's like the new attacks, the 0 days or whatever you want to call them, they're the unknown unknowns, and you can't write a signature for something that you don't know about generally. The second camp there for IDS is statistical anomaly-based detection. Um, this is the machine learning, right? Machine learning is um, either math cleverly disguised as magic or magic cleverly disguised as math. I'm not exactly sure which. It's cool, but the basic idea is that it's creating a baseline for trusted network behavior, and then it will compare new behavior against that baseline using this magic or math. And this technique can be effective in detecting anomalies or novel attacks, things that you're not necessarily looking for. But you have to. It can suffer from high false positive rates, especially if you don't have the um, the baseline there to really define what is normal, which can be difficult in a network assessment, particularly if you're coming in from the point of view of like, I don't necessarily maybe have this long-term network traffic I want to analyze. I just have some pcaps or whatever, right? Um, it can be computationally expensive as well, as far as resources for the machine learning kind of anomaly stuff. Certainly has its place in the threat detection landscape, and there are tools built into Malcolm. Ones we won't really be talking about today necessarily, but maybe at a future video we'll do one for that as well, where we can set up anomaly detectors and start to get that baseline established. But today we'll be talking more about, I think, the third camp, which is where I feel is a nice kind of blend of knowing what I'm looking for versus trying to flag interesting things that I might not be looking for. And that is stateful protocol analysis. Um, Stateful protocol analysis based detection uses knowledge of network protocols to look for deviations from profiles of generally accepted definitions of normal activity. In other words, I know what normal HTTP traffic normally looks like. Usually I see these error codes and these kinds of requests, or I know what SMB file shares do most of the time, and so if I can kind of categorize based on my knowledge of that network protocol, we can programs can then say, hey, here's a summary of what we're doing in this particular protocol or that particular protocol, and it helps us recognize patterns as we look at that data. Um, so what type of intrusions or attacks might we hope to uncover using an intrusion detection system? Let's talk about that. A scanning attack first. A scanning attack is used to detect network topology, to assimilate information about a system or a network being attacked. By attempting connections to a range of IP addresses within a network, or scanning for open ports, which would correspond to responding services on those hosts, an attacker puts together a map of the topology of your network, the types of network traffic that are allowed through a firewall, what active hosts are on the network, the operating system, kernel, and software versions running on the exposed services. This information can then be used to launch attacks aimed at specific vulnerabilities with specific exploits. And a good IDS should be able to notice these kinds of attacks, these kinds of accesses, because they might possibly be seen as a series of sequential connections from one host to a range of IP addresses or ports, or a brute force attempt to log on to some exposed service, and then can alert on that host scan or that port scan that took place. A denial of service attack works by flooding a network or a host with an overwhelming number of connections or requests. So this could be something as simple as sending a large number of ping packets, which is like a ping flood, or by forging the initiation of a TCP connection, a SYN flood, causing the host to be unable to respond to legitimate connections. Intrusion detection systems are usually good at categorizing traffic from or to a particular host or service, and so can often track things like connection state for various network protocols, or at least the number of connections attempts, which makes identifying a denial of service attack pretty easy. It's pretty obvious, I guess, when it's happening that your network is overwhelmed or your host is overwhelmed, just based on the pure volume. And then finally, a penetration attack. This is any type of attack which gives an unauthorized attacker the ability to actually access system resources, privileges, or data by exploiting a misconfigured system or a software flaw. These types of attacks are more difficult to identify because often they look like legitimate traffic, right? Or they may be exploiting, like I said, a misconfiguration or some unknown loophole to get in and get a foothold in the system. Um, and so it's at that point, once they get a foothold in a system and can maybe pivot to another area in the system, it's easier for them to cover their tracks for future communications and mask their commands as normal network traffic. So this is particularly true with custom targeted zero-day exploits or exploits for which the attack vector was not previously known. Um, and hence there's not signatures to detect them. However, IDSs can still be valuable in identifying penetration attacks when they are protocol aware, allowing analysts to recognize changes in patterns of behavior or unusual operations in the context of those protocols within normal network traffic. So Zeek, we're going to talk about Zeek for a little bit. Zeek, which was formerly known as Bro, is one of the two pcap analyzing engines used by Malcolm to generate metadata about network traffic, which metadata is indexed and made searchable through Malcolm's visualization tools. So before we get into what those tools are, let's do a little more laying the groundwork of what Zeek's capabilities are and what Zeek is to better understand what it offers analysts as a Malcolm data source. So where does Zeek come into the picture? What is Zeek? Sometimes it's referred to as Zeek IDS, and it incorporates some techniques from the previous slide, but Zeek is more than just a intrusion detection system, really. It's really great. It's an extensible open source passive network analysis framework, and it does packet capture, traffic inspection, intrusion detection, records flow logs. It can even be used, has a robust scripting and data structure framework for log enrichments or for writing your own, creating your own logs or even writing your own network analyzers. So if I had to categorize Zeek into one of the three detection method categories from our previous slide, I'd categorize it in the stateful protocol analysis detection camp. Zeek's network traffic parsers examine network traffic at the application layer and then reports on the behaviors of hosts that are communicating over those protocols. So these logs can then be used to do a more in-depth manual or automated analysis, as we'll see throughout our discussion of Malcolm today. I would say that Zeek as well is fundamentally different from other IDSs in that it goes beyond pure signature matching in favor of analyzing that application layer behavior of the hosts themselves. Although it does have signature matching capabilities similar to Yara or Snort, generally its focus is more on just parsing network traffic at the application layer. Zeek features can be combined in powerful ways to provide insight into network traffic. With Zeek logs and network analysis, can include content extraction, for example, extracting exfiltrated files from pcaps for further examination, behavior analysis and session correlation. As Zeek is highly stateful, extensively tracking application layer network state, it can be used to determine what else took place during a session or during the communication between two hosts, or maybe what preceded or followed a suspicious event. And then, like I said, Zeek is extensible. Support for uncommon protocols, for example, OT protocols, can be added via scripts and plugin architecture. As I work a lot with analysts that deal, as I said earlier, in industrial control systems or critical infrastructure kinds of networks, a lot of these protocols are not commonly seen, on the internet as a whole. And so a lot of the times off-the-shelf tools that you'll find for dealing with don't include dealing with this kind of traffic. And so one of the things that Malcolm has done with its use of Zeek is add a bunch more support for OT protocols, for ICS protocols, and then allowing us to kind of bring that metadata that's associated with those communications to the forefront alongside the more common IT protocols. So Zeek is a really powerful tool. It's commonly used in network traffic analysis, but it does have its own set of hurdles. And in a minute, we'll hopefully see how Malcolm you'll hopefully see how Malcolm helps overcome those hurdles. While Zeek, for example, Zeek is going to give us that metadata, but it can be difficult for someone who is not, an expert traffic analyst, an expert network analyst, to get back from the Zeek data to the original packet payload. And if you do need to get into the actual low level payload, it can be difficult to go from Zeek to say Wireshark and open that up with just the tools that you might be used to using. One of the other things, right? Zeek it generates a bunch of flat text log files, right? A bunch of delimited or JSON log files, and if you've got gigabytes of text files, there are some tools to manipulate those and stuff. But again, if you're not maybe really well versed on the command line, or if you don't already have a tool set in place to process those text files, it can be difficult to run Zeek and then know what am I supposed to do with all of this, all these logs. So we're going to talk today about Zeek mostly in its context as a component of Malcolm to perform post-capture network analysis against pcap files that we've already gathered previously. So let's talk about the kinds of logs that Zeek generates so that when we get to looking at that data, we can recognize what we're seeing. First, the kind of the backbone of Zeek traffic analysis is con.log. Con stands for connection, and that's what it is. It's network session tracking. Con.log is the backbone of a Zeek analyst, of a Zeek analysis, because each line of con.log, each record in con.log represents a unique network session, which is identified by a four-tuple consisting of originating or source, you can kind of think of it like that, source or originating IP and port, and responding or destination IP and port. So originating IP port, destination IP and port makes up that four-tuple that is a unique identifier for that session. So each connection in con.log, each session, is assigned a randomish 18-character unique identifier, or UID. And so a particular session's UID from con.log will be referenced in any other Zeek log files generated from that same network traffic. So for example, in the case of an HTTP session between a web browser and a website, there may be one line representing the entire session in con.log because that HTTP session is a TCP connection, and it's from an IP and a port to an IP and a port, and then during the course of that connection, there could be many HTTP operations, gets and posts and responses and requests, and each of those actions in the HTTP section, each of those operations will be represented in http.log. So you may have one line in con.log with this UID, and then that UID will tie to many lines in http.log because those requests belong to the same session. And so you can use that con.log UID, that Zeek UID, to find out like what happened across all of my network traffic in the context of this session. So there are a lot also besides con.log of protocol specific log files that Zeek will generate. So taking note of which log files are generated from a network trace can give you insight into what's in your network even before you begin analyzing the file's contents. For example, if I see an SSH.log in a network maybe where I didn't know I had SSH going on or something like that, right? That can be like, hey, I better go look at that because I don't know what that is. And so even just starting at like what log files do I have? What did Zeek generate today on this pcap can give you a good idea of just what traffic is in your network. Zeek has a really powerful file analysis engine that attempts to detect and identify when file transfers occur. So in other words, anytime a file is transferred across one of the protocols that Zeek can understand, uh, Zeek can recognize, hey, this is a file transfer. This is a file being uploaded or downloaded across your network using, HTTP or FTP or SMB or IRC or SMTP email. There's various different protocols that are supported in Zeek's file analysis engine. Similar to connections, each file in files.log is assigned a random file unique identifier, or FUID, that can be referenced in other log files. So very similar to our previous example, a file is transferred by an HTTP request and response, and that file will generate a line in files.log with a unique FUID, and then that could be referenced in the http.log to see the details of that connection, right? So use that UID just in the same way that you use the UID in con.log to reference the session across the entire analysis data set. Use that files.log FUID to reference that file transfer across the various different protocols that it may have been involved in. Entries in files.log can also be linked to the sessions during which they were transferred in con.log by the connection UID. So these two fields, that con.uid and that files.fuid, can be really, really important for getting context about what's going on in a network session. Two specific types of files that Zeek breaks out into their own log files is pe.log. PE stands for portable executable, and this contains entries about file transfers that were done for portable executable files, or in other words, a windows.exe or a Linux ELF file. That might be specifically of interest as a network security analyst, because oftentimes, you may be like, hey, we're not supposed to be downloading executable files or whatever and running them on these systems, on these endpoints. There's also x509.log, which contains information about x509 formatted public key signatures or public key certificates, like you would see in an SSL or TLS session. One really important log file for Zeek, and almost kind of where I would start if I was going to look at a Zeek log, a collection of Zeek logs, would be notice.log. Notice.log is Zeek's concept of an alarm, a big red flag, a way to draw extra attention to an event. So notices can be generated from any other Zeek script or protocol as it's processing traffic. Zeek currently implements, I think, maybe 50 or so notices kind of in its default configuration, and then Malcolm adds several more, ranging from brute force SSH login attempts to SQL injection attacks to expired SSL certificates, and then some of the ones that Malcolm adds for recent CVEs that you may be aware of or have heard of in the news in the last couple of years, events that are categorized according to the MITRE attack framework. So when you see the presence of a notice.log, we'll go check that out and say, what's going on here that Zeek thinks it needs to raise this red flag that I should look at this traffic. And we'll give some examples of those as we get into the demo kinds of stuff here, which my plan is to sprinkle throughout this video. So as you're watching this video on YouTube, or if wherever you got it, um, that's kind of my plan. Is there'll be some demo stuff in here as well. Weird.log. Weird is a good place to begin when looking for anomalous network traffic from the point of view of anomalous in that the protocol itself is not behaving the way that you expect it to. You can some people kind of look at weird as like a notice.log light, like stuff that's kind of strange or maybe not, a little bit out of the ordinary, but it could be, it might be nothing. And so, it's something to look into, but also you need to understand your network in order to, to maybe weed out some of the false positives or things that actually do expect to see in your network. For example, because what's weird in one network might be perfectly normal in another. For example, in some networks that I've been in and seen where old serial protocols are being encapsulated over Ethernet, that may be very common in an aging industrial control systems network that's using serial Modbus or something like that. And then you would see from Zeek a weird.log that's like, hey, I've got non IP traffic over Ethernet. And I look at that in an OT network and I'm like, yeah, this is pretty much what I expect. That's not really that weird. But maybe in your IT network or in your corporate side of your network, that would be unusual, right? So I don't know, one man's trash is another man's treasure or whatever. But you just kind of need to get familiar with your network enough to know really what is weird and what's not. Signatures.log is used to flag hits from Zeek's signature-based engine and is also used by Malcolm to log hits from file scanning engines on transferred files extracted by Zeek. And we'll talk more about that later. And then this one, we won't spend a ton of time on this, but at a configurable interval, defaulting to 1 day, Zeek will dump summary lists of various entities, endpoints, services, whatever, that it's seen over the course of that period. So that might include SSL certificates, MAC addresses, hosts that have performed TCP handshakes, Modbus servers and clients, and TCP, I already said TCP services, but yeah, like what services, what servers are on your network. Known host.log along with con.log can be an essential part of Zeek for building a network diagram or from validating an asset inventory list. Zeek may also generate a software.log, where it can identify software communicating across the network, client server, and if possible, include the actual version of that software. So examples might include identifying Windows operating system versions and clients and servers, communicating over HTTP, FTP, SSH, SMTP, MySQL. And this can be useful during an assessment to identify network hosts or devices that are running software or firmware with known vulnerabilities, and or software that's out of date, right? That hasn't been patched. And when identifying servers by operating system, type of application running, and like I said, the version of that software. So we've talked a little bit about Zeek now. Let's talk about Archime. Archime is the other pcap analyzer used to populate Malcolm's network session metadata database. So Archime has a lot of similarities to Zeek in that it parses network traffic data and generates these sessions, these logs that represent network connections. These Archime session logs are written into an Elasticsearch database where they are indexed and they become searchable. What's unique and powerful about Archime is that these network sessions then can be tied back into that original payload that exists in that pcap file. So that allows for deeper packet inspection and searching that's not just limited to packet headers. So that's kind of the list of components that are put together to make Malcolm, at least the main ones. The components comprising Malcolm are industry standard open source tools, and that makes it easy to integrate Malcolm with other solutions in those tools' respective ecosystems, whether that be importing more Zeek plugins or dashboards into Kibana or whatever it happens to be. Um, I've got a list here of the network application protocols that Malcolm can parse, interpret, um, and there's dozens of them there, as you can see, including several protocols commonly seen in OT networks. Much of Malcolm's development right now is dedicated towards improving Malcolm's coverage of protocols used by ICS devices. So let's kind of talk about the journey that your pcap file will take as it is on its way to being enriched and indexed and user searchable. Upon upload, Malcolm generates the metadata for the network traffic that was represented by that pcap file using both Zeek and Archime's mulloc capture. And so that pcap gets sent two directions. Um, Mulloc capture aggregates its metadata for particular network connections, and it aggregates that into a session record, which is then written into Elasticsearch for us to index. Zeek, as well as we've talked about, generates these log files that are broken out primarily by application protocol, and they similarly contain metadata that is that is not unlike that done by mulloc capture. Malcolm also uses Zeek's ability to carve out files transferred over these protocols, and these files can be scanned, for example, by an antivirus tool or preserved for analysis with other tools, with whatever your tool of choice is. So those Zeek logs are forwarded by FileBeat to Logstash for further enrichment, and it's normalized to the same underlying database schema, the same underlying field schema that Archime uses, so that those Zeek, as much as possible, those Zeek logs and those Archime sessions can be viewed side by side as apples and apples. And then that's indexed into Elasticsearch as well. And then once ingested by Elasticsearch, Malcolm provides two interfaces for visualizing that network traffic. Kibana, primarily for the Zeek logs, and then Archime Viewer, which can be used to visualize the Zeek logs as well as the Archime session data. So now that we have had kind of an overview of the main components of Malcolm and how they fit together and kind of the theory behind what they do, let's get into the process of actually doing network traffic analysis. And that, surprisingly enough, that doesn't start with just uploading your pcap file. You would think that would be the first step. But there's actually one very useful step that we want to do first as much as possible, and that is to identify network hosts and subnets. So for that, there's an interface that Malcolm provides called the Host and Network Segment Name Mapping Interface. And that allows you to assign names for network segments or subnets and hosts, and that might be any kind of endpoint, whether that's a server or a desktop or a laptop or a PLC or an HMI or whatever has IP addresses or MAC addresses on your network. As Zeek logs are processed into Malcolm's Elasticsearch instance, the log's source and destination IP and MAC address fields, which is zeek.orig_h, and that's that naming convention. We kind of hinted at it earlier, but that originating host, that's orig_h. Zeek.resp_h, that's responding host. And then the MAC address fields, orig_l2_adder and resp_l2_adder. So basically, source IP, dest IP, source MAC, and dest MAC. They're compared against the lists of the host addresses provided in this interface. And when a match is found, a new field is added to the log. It's zeek.orig_hostname or zeek.resp responding_hostname. So that orig_hostname and the resp_hostname is added to allow your custom defined host name that you've mapped out to these IP addresses or MAC addresses to be actually written along with those logs. For traffic matching the list of segment addresses provided, Zeek.orig_segment and Zeek.resp_segment fields are added. If both Zeek.orig_segment and Zeek.resp_segment are added to a log, and if they contain different values, different subnets, then a tag, a value to the tags field will be added with the cross-segment value. And that allows you to conveniently identify cross-segment traffic. So at this, maybe right now you're like, my eyes are glazing over. What is this resp_orig_L2? It's really, it's not that complicated. It's just a way for you to say, hey, here's some IP addresses. I want to give them names that I recognize. Here's some network subnets. I want to give them names that I recognize. Right? This is my corporate zone. This is my OT zone. This is my DMZ. Whatever. And then if you can identify what those are ahead of time, upon ingestion of that traffic, Malcolm will tag that traffic as such, and then note when things like cross-segment traffic is happening. Right? If you had a device in your control systems network that is reaching out to the internet, or talking to a device in your corporate network, it would ideally flag that as cross-segment traffic, and you would be able to recognize that without having to go hunt it down yourself. There's a field in this interface called the required tag field, and basically what that is it's a way for you to say, only apply this tag, or only apply this name, this segment or host name, if this tag exists. As we get into uploading pcap files in a minute, we'll talk about how you can apply tags that go along with your uploaded pcap data. So in other words, if for example, I'm uploading a pcap that's represented by representative of a particular facility, and that facility's name is facility ABC. I could tag that upload with facility ABC, and then in this network segment name mapping interface, basically say, only apply this name to this IP address if the tag facility ABC is present. These mappings can also be defined as in a delimited format in cider-map.txt and host-map.txt in the Malcolm installation directory. I would refer you to the Malcolm documentation on GitHub to see the format for that. I hope to be able to come up with a feature in the future where, like, you could take an Excel spreadsheet or something similar and upload it straight into this interface and have it magically figure stuff out for you. It's not quite there at this point, but that's something that maybe we can look at doing in the future. So we're going to go ahead and do our host and network segment mapping now, and I'm going to do that by navigating on the Malcolm web interface to my Malcolm instance is running on localhost, and the name map UI is the interface that I'm interested in. And since I was previously authenticated before I started recording this, I didn't have to put in my username and password. Now, if I was going to start doing this from scratch, depending on how big my network is, I'd either just start typing IP addresses in, one at a time, something like this. Then click save, or maybe another segment, home network. We're going to call 1.2.16.0.0/12 or something like that. And this is home network, etc. In this case, for our example, I've already created a network mapping for the pcap that I'll be using for our for this demonstration. So if you've done that before, you can actually save that and back that up and then restore it later, which is what I'll be doing now. So I'm going to click import, and I'm going to replace the name mappings with this netmap.json file that I previously created that already corresponds to this pcap. I'm going to do that, and you'll see that it populates my list here with segments and hosts that make up my network map. As you're doing these, you can also you can search the list. For example, if you want to come back later and look up, what you created as your you want your list of, historians or something like that, I can start typing historian here, and it'll filter that list, or just any text that's available here. We can start typing that, and then it will filter that list. But once we've defined our host and network name mappings, we're going to go down to the bottom of this list. We're going to click Save, and click Yes to save our name mappings. And then what we're going to do is, before that will take effect into our name ingestion, into our pcap ingestion, we will need to click Restart Logstash. And it will tell us, make sure that we actually want to do that, want to apply the save name mappings and restart Logstash. And if we do that, it says Logstash ingestion is restarting in the background. Log ingestion will be resumed in a few minutes. And I can click OK. And at this point, after I wait a couple of minutes and wait for Logstash to come back up, we will be able to continue with our upload and make sure that those IP addresses are mapped to the names that we've specified here. Once we've defined our network subnets and host names, we're ready to upload that pcap data. Elasticsearch is a write once, read many kind of mentality of a storage platform, and so we can't upload pcap data and then go back after the fact and apply those network and host names. We need to have that ahead of time so that we can enrich that data as we're doing it. And so if you come up later and you say, "Oh, I didn't do my network hosts or whatever," it's not like a huge deal. Malcolm generally is pretty quick to analyze network traffic, and so what I would do is wipe that data out, clear the database for Malcolm, and then apply my network subnets and host names and just re-ingest the data. Is kind of the workflow that we generally see. So once we've done that, Malcolm must be provided with network capture, network traffic to analyze, right? In other words, a pcap file. So we've talked a little bit how that could be done with dedicated network sensors like Hedgehog Linux. Oftentimes, though, in an assessment, you'll be given pcap files that have been previously captured and provided to you as network security analyst, or that you have captured at some other point in your network or some other point in the past, and you're bringing in to analyze now. So pcap files can be uploaded to Malcolm by processing by accessing the upload interface, so whatever your Malcolm IP address /upload on the host at which Malcolm is running. Prior to starting the upload, as I mentioned, you can add tags which will allow the data from the pcap files being uploaded to be searchable using those tags later on. There's also some other behavior here on how the pcap file is parsed with regards to whether you're analyzing it with Zeek or whether files are being extracted or not. Generally, I like to set these in the configuration options so that they're just done globally and I don't have to mess with them here. But if you want to override the global behavior that you've set during configuration with as far as the Zeek and Zeek file extraction goes, you can do that here in the upload interface. We're going to upload our pcap file now by navigating to the localhost /upload, and that's going to present us with the Malcolm capture file and log archive upload interface that we just discussed. I have got my pcap file here, and so as it uploads this pcap file, I talked about the tags it's going to apply. So if I wanted to tag this with, for example, I'm doing this for this training video, so I could create a tag called training, and it would add that. Or if this was a particular site, site ABC, customer 123, incident, omega, whatever. Oops, you got the idea. Anyway, I could apply whatever tags I want here, and those tags would be searchable after I do the upload. Additionally, Malcolm will take and create tags from the name in the pcap file itself. So in this case, where the pcap's file name is cyberville.pcap, the tag cyberville will automatically be applied. So I'm not going to create any additional tags here. I don't really need any besides this default one that I've got from the file name. But I could add as many other pcap files as I wanted to here if I had multiple pcap files. and then once I'm done, I can either start them individually or just click Start Upload. Um, Before we take a harder look at Kibana and Archime's user interfaces, let's talk for a moment about the fields that Logstash can use to enrich log data before it's written into the database. So, in other words, there's a lot of stuff that we can infer from our network session metadata that might not initially be in that data. MAC addresses, for example. MAC addresses can generally be mapped to a hardware vendor, as the first three octets of a MAC address uh, are called an OUI, or Organizationally Unique Identifier. It can be used to distinguish a network card that was manufactured by Intel from one manufactured by Dell, or a VMware network interface, or an interface on a Schneider PLC or whatever. Um, this MAC address then is used to look up that vendor, and that's added into that log whenever possible. Malcolm also can be configured to do GeoIP and ASN lookups for IP addresses. We can identify internal and external traffic based on IP ranges, or in other words, private IP ranges versus publicly routable, globally routable IP addresses. Malcolm can do reverse DNS lookups. It can do DNS query and hostname entropy analysis in order to detect DGAs, or domain generation algorithm host names, that are often used by malware. So some malware will use for you can go read it on Wikipedia or whatever, right? Look up domain generation algorithms. But basically, the malware generates this long giant uh, host name, or URL or whatever, that is like a whole bunch of characters, letters, and numbers, dot a whole bunch of ugly stuff, and that high entropy, that randomness in that URL host name, or that DNS lookup or whatever, can be used to can be bubbled to the top for your analysis. The other kind of things that we'll do on enrichment with Malcolm is community standard fingerprinting algorithms to be applied whenever applicable, so that can make Malcolm's data cross-referenceable with other tools. One really good example of that is a flow hashing technique called Community ID that basically takes the relevant stuff in a network connection, IP addresses and ports primarily, and generates this unique hash of that flow. And then that hash can be used to cross-reference logs from not only inside of Malcolm, Zeek, and Archime, but off to Suricata, or whatever other network tool that supports Community ID, and it's quite a long list. The other one that I would mention, we've already kind of talked about this, is enrichment is done to populate that tags field with each log. And some of the tags that I would make particular note of would be these ones that are listed here: the internal source, internal destination; external source, external destination. Those are hopefully self-describing or whatever, but to identify traffic that is on a private subnet, your 192 dot, your 172 dot, your 192.168 dot, your 172 dot, and your 10 dot IP address ranges versus globally routable IP addresses. And then that cross-segment one, if you've defined your network segments in the previous interface that we talked about, that cross-segment tag will be applied whenever it sees traffic in the Zeek logs that crosses one of those network segment boundaries. Once you've got data into Malcolm, it'll take, once it's been processed after a few minutes, you'll start to see logs trickle in, and you can visualize that log data. Kibana is one of Malcolm's two user interfaces for visualizing log data. Where Kibana really shines for me is in providing an intuitive, interactive representation of log data that that simplifies the process of starting at like this high level, and then being able to drill down quickly to stuff that is interesting to you. So filtering from this big pile of hay, and you're looking for the needle in the haystack, to like a much smaller pile of hay that makes it easier to find the needle. Being able to quickly drill down on an individual host or connection of interest. Malcolm comes with dozens of pre-built visualizations specifically for data ingested from its Zeek logs. Its dashboards fall into two categories: overview dashboards and protocol-specific dashboards, and we'll review some of those here in a minute. And aside from the pre-built dashboards, Kibana provides an easy drag and drop WYSIWYG editor for creating new visualizations on the fly. Now, the key to effectively using Kibana is learning how to apply filters, how to search the data. So as we talk about applying filters, like you'll be using these patterns throughout all network traffic analysis in Kibana to do what we just talked about, to start from this big picture and drill down into something, to zoom in on something of interest. The first step to applying filters is identifying the time range of interest. This can be done by using the time filter controls that are in the upper right hand corner of the interface. And this is me as much as anyone else I've ever seen, but oftentimes if I'm not seeing the traffic that I want to see, and I'm like, where's my data? It's because I'm searching on the wrong time frame, right? It's because I captured my pcap 2 weeks ago for analysis and I'm finally getting around to it, and like the default controls for Kibana are like set for the last 15 minutes or something like that. So always check your time frame in that in those time controls in the upper right hand corner, and then you can use that time histogram that like logs over time graph that you'll see on most of the Kibana interfaces, most of the dashboards, to zoom in or zoom out based on what time frame you're interested in. Additionally, the query bar allows you to specify search constraints. And you can do that using a couple of different syntaxes, actually. The traditional Lucene query syntax or the new KQL Kibana query language syntax. And in the documentation and in some tables that I'll probably include here in this video, you'll see maybe some of the differences in those syntaxes. And there's really no magic bullet other than just having the reference bookmarked and then getting used to what that syntax is for creating your queries. Modifying the contents of this search bar and then hitting enter or clicking the search icon to the right of it will run the search and update the results that are displayed. So, the time filter, that search query bar, and then finally the filter bar, which is more GUI kind of based filter creator underneath the search bar, is the third way of specifying search constraints. Although it provides more of a GUI kind of interface to do so, it's generally not quite as like freeform or flexible as writing textual queries. In most cases, there's not really a meaningful distinction between putting query terms in the query bar versus the filter bar. What the filter bar does allow you to do, which is nice, is allow you to pin those filters so that when you navigate from one dashboard to another, those filters stick around, and the ones in the query bar generally don't. The filter bar is also what's populated when you click on values in the charts or tables. So whenever you see a value in a chart or a table in a Kibana visualization, you mouse over it. There'll be like a little magnifying glass with a plus icon or a minus icon in it. So you can use that to create or exclude filters, or create filters for or filters to exclude those values based on what you want to see or don't want to see in that result set. And as you click those magnifying glasses, you'll see the filter bar is updated to reflect that filter. I've read that a future release of Kibana will merge the query bar and the filter bar into like one component. I'm not exactly sure how they'll do that, but I guess that's something we have to look forward to. Let's talk about the overview dashboards. The dashboards under the general section of Malcolm's Kibana interface provide a high-level overview of network traffic from across all of the logs generated by Zeek. In other words, they're not restricted to like a particular application protocol. These dashboards are a good jumping off point for investigation when you're trying to get a feel for the network and application protocols uh, and the hosts that are on that network and using those protocols. One of note is the notices dashboard. Um, as discussed earlier, Zeek notices are the tool's way of raising some event to the forefront of an analyst's attention, um, and those notices are summarized here in the Zeek notices dashboard. Um, the third-party Zeek plugins that Malcolm uses to generate additional notices or to analyze traffic in different ways can be found in the Malcolm README on the Malcolm's GitHub page. They include some of the interesting ones, they include but aren't limited to notices that are generated for clear text passwords detected in HTTP post requests, non-compliant HTTP post requests, non-compliant HTTP requests, like those that might be used for, for HTTP smuggling, XOR obfuscated file transfers. I mentioned this earlier, but behavior or techniques categorized according to the MITRE ATT&CK framework. And then like lots of various other CVEs and vulnerabilities, bad neighbor, call stranger, SIGRED, zero logon, the ECC certificate validation, uh, and the new TLS unencrypted session ticket dissection, the Eternal family of Samba Windows exploits from SMB v1, which includes Eternal Blue, Eternal Synergy, Eternal Romance, Double Pulsar, uh, other various SMB exploits, Ripple 20. So the developers of Malcolm endeavor to stay abreast of developments in the threat landscape, and whenever possible, we release updates that include new Zeek plugins to detect or scripts to detect these vulnerabilities and exploits as they are discovered. Another interesting dashboard from a security standpoint, a pair of dashboards actually, is the security overview dashboard and the ICS/IoT security overview dashboards. These highlight events that may be of particular interest from a security standpoint, including Zeek notices, signatures triggered from file scans, clear text transmission of passwords, outdated or insecure versions of application protocols, traffic originating from or directed to public IP addresses, types of files transferred, and more. These dashboards can be a good jumping off place when looking for indicators of compromise in your network or vulnerabilities in your network traffic. Where possible, Malcolm correlates common fields from across different protocols to allow you to view one device or application's network traffic in the context of the other traffic occurring around it. For example, multiple failed HTTP authentication attempts followed by a successful authenticated HTTP post operation, followed by, sequential reads and writes to a file server could indicate that a foothold was obtained in an HTTP server that allowed the adversary to pivot to another service on the network. So a good example of this is the actions and results dashboards, in which actions, a lot of network protocols have the concept of action and a cause and effect, action and result, request and response, whatever you want to call it. And so actions are things such as a file was written, a logon was attempted, a web page was requested, and then the results would be success, access denied, page not found. Across all the protocols that I can figure out what those actions and results are, I normalize those to the same fields so that in, for example, the actions and results dashboard, you can see actions and results across all these different protocols together. In addition to the overview dashboards, Malcolm provides dozens of dashboards tailored specifically to application protocols, including protocols commonly found in industrial control system networks, as well as those found in more traditional IT kinds of networks. The Discover view, Kibana's Discover view, enables you to view events on a record-by-record basis, similar to a session record in Archime, which we'll discuss in a moment. In other words, the Discover view allows you to look at an individual line from a Zeek log, an individual record from a Zeek log. The data table in the Discover view can be customized to display only the fields that are relevant to the traffic that you're interested in. So for example, if I wanted to put together a play-by-play of an HTTP session, um, rather than looking at this big JSON log that contains all of the fields that may not be relevant to my traffic right now, I could go to the Discover page, filter on Zeek.log type for HTTP, sort by time, and then include source IP, user agent, referrer, dest IP, and then the HTTP host URI and status message, right? And by doing that, I've got a more focused view of HTTP traffic that I can then go through and see this happened and then that and then this. And then once I've got a configuration that I like for a particular kind of traffic, I can save that search as HTTP traffic analysis or whatever I want to call it, and then return to it for further investigation in the future. The visualizations page allows you to view and manage visualization components, which are like graphical building blocks to be used in dashboards. Kibana includes lots of different kinds of charts, tables, maps for displaying your data. While Kibana is great for at-a-glance views and for creating custom visualizations, Archime, which until recently was known as Mulloc, provides another interface for examining network traffic that may be better suited to in-depth analysis and network forensics. Earlier when we talked about the Malcolm pcap processing pipeline, we mentioned that pcap data got sent two directions, right? It got sent to Zeek, and then it also got sent down to Mulloc Capture, which is Archime's program for ingesting that data. While Malcolm's Kibana dashboards are focused on the Zeek logs, and the Archime sessions won't necessarily be reflected there, Malcolm's instance of Archime can be used to view both Zeek logs and Archime sessions together in the same interface. Another really great strength of Archime, and I mean arguably its kind of initial reason for existing, is as a full pcap solution, right? Its ability to tie the session metadata back to the original packet's bytes, the original packet payload, which allows you to view and search and export the data deeper in the pcap that may not be referenced in the metadata. So Archime, what it really allows you to do, which I think is so incredibly powerful, is efficiently deal with very large pcap file sets and still have access to the underlying payload data, something that Wireshark struggles to do. So similar to Kibana, we want to learn how to effectively build filters in Archime to narrow in on the data that's of interest to us. So we've got at the top of the Archime interface, you've got controls for specifying your time filter to define your time search frame, your search time frame. And just like in Kibana, that's very important. Make sure you know what the time frame of the data that you're looking at is. There's a little globe icon that can be clicked to expand a map filter that allows you to restrict results to a geolocation, which may be of interest if you're looking at data that is going out to the internet. There's a query bar where you can specify queries in Archime syntax. And then to the right of the search button, there's this eyeball, the views button. And that allows you to overlay previously specified filters onto the current sessions filters. And so for convenience, Malcolm provides several Archime pre-configured views, including some that involve the Zeek.log type field, so that in Archime, as we're viewing both Archime sessions and Zeek logs, you've got a quick way to say, hey, right now I only want to look at Archime sessions that are tied to pcap files, or I want to look at Zeek logs that were generated from pcap files but don't leak directly back to the payload like the Archime sessions do. So you can see those here, some of the views that Malcolm has pre-configured for us. Archime's Sessions tab provides low-level details of the sessions being investigated in a way similar to how Kibana's Discover interface does it. And in the sessions view, you will see Archime sessions that are created from pcap files, and then that Archime session log is written to the Elasticsearch database. And you'll see Zeek logs mapped to that same Archime session database schema, and you'll see those together in the same pane of glass. It should be noted that you can distinguish between the two by the value in or the absence of a value in the Zeek log type column in the sessions table. Similar to how we did with the discussion to the discover table earlier in our discussion, you can also customize the set of fields present in the sessions table, and then save or later recall those configurations of fields that you're interested in to exist in that table. As mentioned, Archime's ability to tie a session record back to its original packet is one of its greatest strengths. So details for an individual session or log can be expanded by clicking on that plus icon on the left-hand side of each row in the sessions table. For Archime sessions records, an additional packet section will be visible underneath the metadata section. When the details of this section when the details of a session of this type, in other words, an Archime session, are expanded, Archime will reach out to where the pcap is stored and extract the payload for that session for display here. Various controls can be used to adjust how the packet is displayed. Personally, I like to enable natural decoding and click show images and files. And that produces visually appealing results to me for when I'm looking at payload data. But there's lots of options there. Other options also become visible when you have pcap data available, when you have that pcap session data to be extracted for the payload. And that includes downloading the pcap itself, downloading and generating, carving out, if you will, a pcap for that particular session, carving out and downloading or viewing images and files, applying decoding filters, and examining payloads in CyberChef. All of that can be done from this packet payload section. Back up at the top of the interface, if you click the down arrow to the far right of the search bar, you'll see some new actions presented there, including pcap export. When full pcap sessions are displayed, the pcap export feature allows you to generate a new pcap file from the matching Archime sessions, including controls for which sessions are included. In other words, open items, only the ones that I've actually got expanded right now, visible items, which is everything that I'm seeing on this page right now, or all matching items, everything matching my current search filters, and then whether or not to include linked segments. Once you've defined how you want to do that, what your filters are, and then which sessions you want to include, click the Export PCAP button to generate the PCAP, and after which you'll be presented with a browser download dialog to save or open that file in Wireshark or whatever it happens to be. Note that depending on the scope of your filters, this could take a long time, right, to generate that PCAP file, or it might even time out. So it's a good practice to look at the number of matching sessions there on your Archime sessions interface before you go exporting a PCAP. And if it's like, hey, this is 1 billion sessions, I may want to apply further filters before generating that PCAP file to further narrow my search. Note here as well, and this is kind of a known issue that I hope to be able to figure out a way to resolve, but you will probably get an error if you try to do an export PCAP without applying the PCAP files view with that little eyeball icon to the sessions first. There's a bug in what I'm doing, I guess, or something that when it tries to export a PCAP file from logs that don't have PCAP associated with it, you might get an error. So if you'll apply that PCAP files view first, you'll make sure that error is avoided. Moving on from the sessions interface, we're going to go to Archime's SPY view. SPY stands for Session Profile Information, and the SPY view provides a quick and easy to use interface for exploring session or log metrics. basically, what the spy view page does is list categories for general session metrics like protocol, source and destination IP addresses, source and destination ports, and also like all of the various different network protocols that are understood by Archime and Zeek. So whether it's HTTP or SNMP or BACnet or whatever, these categories can be expanded and the top N values displayed for whatever field of interest uh, exists there, including that field's values cardinality. In other words, it's a good like top talkers, top N, whatever display of any field of interest for you in Malcolm's logs. And between Archime and Zeek data sources, Malcolm's list of fields that are available for you to check out here in the spy view is over 1,300 different fields across all these different kinds of network traffic. So click on the plus icon to the right of a category to expand it, and the values for specific fields are displayed by clicking that field's description in the fields list underneath the category name. That list of fields can be filtered by typing part of the field name in the search for fields dialogues to display in this category text input. The load all and unload all buttons can be used to just like bring forward everything that it knows about that protocol at once. But you may want to be careful with this as it is going to run a lot of queries and it might take a while. So, you know, if you know you actually want to see everything, yeah, go ahead and smash that load all button. But it might, you know, end up giving you more data than you really want depending on what your interests are. Once displayed, a field's name or one of its values can be clicked on to provide further actions for filtering or displaying that field or its values. So of a particular interest might be the open field name spy graph option when clicking on a field's name or pivoting to another sessions tab with that field filtered. That'll open a new tab with the spy graph populated or the sessions populated with that filter already applied. Note that because the SpyView page can potentially run many queries, SpyView limits the search domain to 7 days, or in other words, 7 indices, as each index represents 1 day's worth of data in Malcolm. So when using SpyView, basically that means you need to limit your search time frame to less than or equal to 7 days before you flip over to this tab, or it'll complain at you for doing that. Spy graph is another really cool way to visualize the top N field values of a particular field, both chronologically and geographically. So spy graph, session profile information graph, visualizes the occurrence of whatever field's values over time. And for me, that's particularly useful because it helps me identify trends in a particular type of communication over time. When I'm looking at just kind of the conglomeration of all of the traffic over the date histogram there up at the very top, it's hard to pick out patterns for a particular protocol or a particular IP address or user agent. So traffic, for example, using protocol as an example, traffic using a particular protocol when seen sparsely at regular intervals on that protocol's date histogram in the spy graph could indicate, you know, a connection check or polling or beaconing, and having it split out by protocol, by value like that, is very useful. But it doesn't have to be protocol. It can be any of those 1,300 fields that Malcolm knows about. You can set as kind of that pivot value for the spy graph to split out those top N values and show you chronologically and geographically where those took place. Controls can be found underneath the time bounding controls for selecting that field of interest, for the number of elements that you want to be displayed, for the sort order, and for if you want to periodically refresh that data view or not. One of my favorite ones to play around with is the connections view. But also just from being cool, it is very useful. The connections view presents network communications via a force-directed graph. So it makes it easy to visualize logical connections between these logical relationships between network hosts or between subnets or between again, any fields, any of these 1,300 different data points that we have, you can visualize kind of how the traffic goes between source and destination based on that field's values. Controls are available for specifying the query size. So this again can run a lot of queries, and so by default, like with the query size set to small, which is like 100, I think is the default. Um, it'll run faster, but you actually may not be getting all of your data, right? So what I like to do is set up my other filters and get everything kind of the way I want it with my query size set to small. And then once I've got it all set the way I want it with my filters and my views and like the source and destination nodes set to the fields that I'm interested in, then I will increase the query size to like the max value so I can see everything that I'm interested in there. But that will take longer to execute, right? So you can select the query size, you can select which fields to use as the source and destination for node values, you can set a minimum connection threshold, the method for determining the weight or the thickness of that line between the nodes and the sides of the nodes themselves. As is the case with pretty much every other visualization in Archime, that graph is interactive. So by clicking on a node or clicking a link between two nodes, you can apply or modify filters. You can reposition the nodes themselves by dragging and dropping them. A node's color indicates whether it's communicated as a source or a destination, an originator or responder, or both. So while the default is source and destination IP for those fields, the connections view is able to use any combination of any of the fields that Archime knows about. So some that I have found interesting or useful before, selecting source OUI and dest OUI to view which devices from which hardware manufacturers are speaking to each other. Source IP to protocol can be a good way of visualizing what hosts are communicating to what servers out there based on the services that they provide. Maybe originating network segment and responding network segment. If we populated our network segments at the very, very beginning before we even created our pcap file in that define network host and subnet name interface. Maybe originating GeoIP city and responding GeoIP city could be interesting to see where my source and destination traffic is going out to on the internet. So any of the combination of these or other fields can be used to specify that source node and destination node in the connections view. Another cool recent addition to this feature, and one that actually we developed here at the INL and then contributed back upstream to Archime, was the ability to specify a baseline time frame in the connections view and then use that baseline to visualize changes to a network over time. In other words, new hosts or protocols that appeared in my network this week that didn't exist last week. This feature is mainly useful if you have prior long-term packet captures available in order to establish that baseline, right? In order to define what my previous time frame is versus what my current time frame is so that you can do that comparison. Another really cool feature of Archime that allows you to get access to the payload data and actually search the packets themselves versus just the session metadata is the hunt feature. You can kind of think of this as like a pcap grep. The search string that you specify for the hunt filter can be specified with ASCII, with or without case sensitivity, hex codes, regular expressions, and basically you create this packet search job on the hunt page with the filters and the other parameters that you're interested in to limit that search scope to make that packet search go a little bit faster. And then once that hunt job is complete, it runs in the background, but once it's complete, it tags matching sessions with that hunt ID, and you can go view the sessions or the matching payloads in the sessions view. So note that whatever filters you specify in the search bar when that hunt job is created will also apply to the hunt job as well. So if I'm over on the sessions view and I've got a filter in the query bar and I switch over to the hunt view, those filters limit the search of packets, the search of the scope of the packets, the scope of the search of the packets that I'm looking at in that hunt job. Um, and so pay close attention to that. There's a little like information icon that says creating a new packet search job will search the packets of 1 million sessions or whatever that number is. Just be aware of what that number is because your hunt's execution time will be directly related to how many packets it needs to go out and look in. Note that the hunt view is only available for sessions created from full packet capture data, not Zeek logs. In other words, Archime sessions only, not Zeek logs. So it's a good idea again here to apply to click that eyeball icon, click the view eyeball, and select the pcap files view to exclude Zeek logs from your candidate sessions prior to using the hunt feature. A couple of notes on correlating data sources between the Archime and Zeek data sources. Note that because these are different tools developed by different organizations for different purposes, the search syntax between Archime and Kibana is different, right? Malcolm is utilizing both of these open source tools together, but in some cases, in all cases really, the search syntax will be a little bit different between Archime and Kibana, and in some cases, the field names themselves will be a little different. So refer to that documentation, refer to that table that we showed you earlier to compare, like, how do I write a query that searches an IP address based on its presence in a subnet, or for sessions that include that subnet, or for how do I do a regular expression or whatever, because it won't necessarily be the same in Archime versus Kibana. As I mentioned, Archime uses its own field names in its user interface. For example, in Archime, you would search protocols equals HTTP, but in Kibana, the equivalent search would be protocol : HTTP. So going to Archime's help, which is the click on the owl icon in the upper left-hand corner, and then go down to the fields section, which is at the bottom of that help page, and click database display database fields, can help you map what Archime's field names are to what the underlying database field names are that the Zeek logs might use. As much as possible during ingestion, we do try to map those Archime fields the Zeek logs to their corresponding Archime fields. But it might help to know, like, if I'm jumping from Archime over to Kibana and I want to know what fields it was actually searching when I was in Archime, you may need to do some manual mental mapping of the Archime field names to the underlying database field names. Also, despite considerable overlap, especially for common protocols, there are differences in protocol parser support between Zeek and Archime. Notably, Malcolm's configuration of Zeek parses a lot more ICS protocols than Archime does, because that's one of the main focuses of this project. So we've looked at these two different interfaces to analyze that same underlying the session metadata from our network traffic. We've taken this one pcap, and Archime has generated its session records, and Zeek has generated its logs. And how can we correlate the two? How can we bring them together and see, like, get the strengths of both tools, right? Get the information about the protocols and stuff that Archime maybe doesn't have support for from our Zeek logs, but then at the same time be able to see the Archime sessions that correspond to those events of interest or whatever they are from the Zeek logs, so that we can get down, if we want to, and see the payload and do analysis kind of at that level. So as I mentioned just in the previous topic, like, one of the things that Malcolm does to try to facilitate this is it maps, wherever possible, Zeek fields to corresponding Archime fields in the database schema. But then for any protocols or fields where Archime doesn't already have native support, Malcolm creates a native database, a native data source type, I guess, for that kind of Zeek log for all these other Zeek log values for which there's not currently support or an equivalent in Archime. The fields section of Archime's help, which I referenced a few minutes ago, can provide a list of all of those known fields across both the Archime and the Zeek data sources. So in this way, when full packet capture is an option, analysis of pcap files can be enhanced by the additional information Zeek provides. Why I say when pcap full packet capture is an option, there may be cases where, for whatever reason, whether it's size constraints or you know, sensitivity of the information, like you may be able to capture Zeek logs, just Zeek logs, and actually not store the full pcap. So in that case, Malcolm can still be used in both the Archime and the Kibana interfaces, but when you have the full packet capture available to you, you are able to, enhance that full packet capture beyond just what the Archime session is giving you with the Zeek logs as well, versus the Zeek logs just being alone. The values of the records that are created from Zeek logs can be expanded and viewed like any native Archime session by clicking that plus icon to the left of the record in the sessions view, just as we showed you when we were talking about the sessions view. However, note that when you deal with those Zeek logs, these Zeek records, the full payload, that section on the packet payload, it doesn't exist, right? Because the packet contents aren't available. So the buttons that deal with viewing and exporting pcap information don't behave the same. They don't do anything basically as they would for records with pcap files. Other than that, though, Zeek records and their values are usable in Malcolm just like their native Archime session counterparts. A few fields of particular mention that help limit returned results to those Zeek logs and Archime session records generated from the same network connection are community ID and Zeek's connection UID. We've mentioned both of those earlier. And we can talk about how, let's talk about how we can use those to get kind of that full picture, right? So the example that we're talking about here is something interesting happened on my network. I want to see in one list everything I know about it. I want to see all of the Zeek logs, and I want to see the Archime session or Archime sessions that corresponded to it. There's kind of a hard way and an easy way to do that. The hard way would be, find the logs that I'm interested in or whatever in Kibana, or however I want to do it, and then say, okay, I've got this source IP and that des IP and this port, and it happened at this time, and just kind of try to handcraft your filters to include everything you want but nothing you don't want. And that's difficult to do. But what we can do is we can use this Zeek connection UID, Zeek.UID, and that community ID, and we can use that to kind of build a query filter that includes everything that has to do with that session across both Zeek logs and Archime sessions. Community ID is a specification for standard flow hashing published by Corelight, and the intent is to make it easier to pivot from one data set, like Archime sessions, to another data set, like Zeek con.log entries. In Malcolm, both Archime and Zeek populate that community ID value, which makes it possible to filter for a specific network connection and see both data sources results for that connection. That Zeek.UID is also mapped to another Archime database field called root ID, so you can use Zeek.UID or root ID interchangeably. That root ID field is used by Archime to link session records together when a particular session has too many packets to be represented by a single session. When normalizing Zeek logs to Archime schema, Malcolm kind of piggybacks or hijacks on root ID and stores that connection UID to cross-reference entries across Zeek log types. So that's interchangeable, Zeek.UID or root ID. So the cool pattern that I want to kind of get across here in this example is by filtering on the community ID ORed with the Zeek UID, so community ID equals some horrible long string, or pipe root ID equals some different horrible long string that represents the Zeek UID. That will cast this tent, which will include both the Archime sessions and the Zeek logs that are generated by this particular network connection, and you can see them together in one place. One item that was mentioned earlier, but we didn't really get into the details of how it works, is the Malcolm's ability to analyze files that are carved from network traffic. As I did mention earlier, as I referenced this feature, Zeek can carve files from a variety of protocols in observed network traffic. And then those files can actually be extracted and stored temporarily locally by Malcolm for analysis. Malcolm leverages that feature to submit these carved files to a number of file scanning tools. ClamAV, for example, which is an open source antivirus engine, can be used to scan for known malware signatures. Yara, the pattern matching Swiss Army knife, scans the files using a curated list of security related signatures or your own custom Yara signatures that you can write. Kappa, which is a portable executable capabilities analyzer, and VirusTotal, an online database of file hashes. Now, to use VirusTotal, you do have to specify your API token, and you would need to have an internet connection for those to be submitted, for those hashes to be looked up. So Malcolm can be configured to there's a couple different other configurations with the file scanning behavior that you can set. Number one, you can set which kinds of files you extract and scan to begin with, meaning, do I want to scan all files? Do I want to scan files that are just of MIME types that may be of particular interest when it comes to security standpoint, right? Things like zip files or executable files or PDF files that might be vectors for common known attacks. And then in addition to which files we scan, we can specify which files we want to preserve, if any. In other words, do I want to preserve all files and then to get stored in this directory locally on the Malcolm instance? Or do I want to only preserve files that get hits from the scanning engines that might be flagged as suspicious? Or do I not want to preserve files at all? And then those files, if they are preserved, can be downloaded from that directory where they were preserved, and then you can do whatever further examination you want on them, whether that's submitting them to other file scanners or reverse engineering them with Ghidra or IDAPRO or whatever your tool of choice is there. As the files are scanned, if Zeek file carving is enabled and those scanners are turned on, questionable files will be written into the signatures log and reported on the signatures dashboard in Kibana. The signatures dashboard will break it down by the scanning engine and then also the name of the signature or rule that triggered on that file. The Zeek connection UID, zeek.uid, and file UID, zeek.fuid, fields in these logs, in the signatures log, can be used to cross-reference to other visualizations to provide the context for how that file was transferred. So in other words, finding on the signatures page a reference to a zeek.fuid for a triggered signature, filtering on that Zeek fuid, and then jumping over to the files.log to see what is it about this file that I know, how was it transferred, how big was it, what other dashboards might reference that file, that sort of thing. Just a few search tips before we close out here. To effectively search in Kibana and Archime, number one, always check your search time frame. If you're not seeing the data you're expecting to see, often it's because the data lies outside of the window of time that you're searching. Number two, this effective technique for investigating is zoom in. For example, narrow in on a particular type of file that's transferred or a particular host. Once you find something of interest, pivot to another field. So select the source IP address that was the source of this file transfer, and then zoom back out by removing the file type filter to see what other activity that source IP was involved in. That's a very effective way when dealing with a large data set, is you find some value that's of interest to you, zoom in on that value, see the other values in context with that, and then zoom back out by filtering on these new values and removing the original filters. Remember that most elements in Kibana and Archime are interactive and can be configured to work with any of the more than 1,300 data fields that Malcolm knows about. So generally in Archime and Kibana, if you can click on it, you can create a filter or you can pivot to some other view, and you don't have to go find these things manually. Uh, you know, don't save yourself some work by learning to create filters from the graphical interface, rather than just having to go remember and, oh, what was my query string that I was doing before, and then get to it that way. Um, Learn how to filter on common fields like Zeek.log type, um, the source IP, dest IP, source port, dest port, protocol field, action and result, OUI, source OUI and dest OUI. These fields that get normalized across all of the different log types that we can do with Zeek. Um, you know, you're not going to memorize all 1,300s of the fields that we have, uh, that we could populate in Malcolm. But as you start to become familiar with those most common ones, uh, learn to build filters around those fields, and you'll become more effective in your searching. Finally, don't forget about that tags field. Um, Using pre-populated tags like the ones that we do during enrichment for the private and public IP space, the tags that got generated when you uploaded your data, the tags that got created during the segment mapping stage of enrichment. All of these tags, including tags that are populated automatically based on pcap file name. Learn to search on those tags. Apply filters on the tags field, and you can easily narrow to cross segment traffic with tags equals cross segment, and it's much harder to do the same thing with source IP in 192.168.0.0 slash whatever and dest IP in 10 dot whatever dot whatever. Like, yeah, you could do it that way, but it's going to be a lot easier just to use the tag that's already populated for that field. I hope this was a good kind of Malcolm 101 course for really starting to get down and get our hands dirty on with pcap analysis. Uh, I enjoy maintaining this project and showing people how to use the tool. If you've got feedback for me, reach out on GitHub. Uh, Reach out via, if you want to, in the YouTube comments, or get in touch with me any other way you can figure out, and let me know what you think. We're interested to know how the community is using the tool and ways that we could improve it. Thank you for your time, and happy hunting.